My name's Dylan Beattie, and the first computer I ever had was this. It was an Amstrad 6128, and it was not a very good computer. My dad brought this thing home from work, and I spent a couple of days trying to figure out how to get it to play games and stuff. And it was not a great gaming machine, but it shipped with a language called Logo. And I loved Logo, because using Logo, I could get the computer to draw pictures. I could make it draw circles and lines and curves, and I learned how to do functions and how to get things to repeat. And that gave me, I never went back to playing games because I was hooked. This ability to sit down and write some code and get the computer to do what I wanted it to do, I got a buzz out of doing that, which for me has never, ever gone away. And what I am going to talk to you about today is that. It's code. It is writing computer code for the sake of making something happen just because you think it's cool. Just like I did back on my Amstrad all those years ago in the 1980s. Now, there is a famous quote from, that's the computer I built this stuff on, and there's a famous quote from Oscar Wilde: all art is quite useless. And he followed up on this, and he's like, no, the whole point about art is it doesn't do anything. Like, if you look at a piece of art and then you go out afterwards and you do some work, the art failed. The whole point of art is to inspire you to appreciate what it is. And over the last couple of days, you've seen some fantastic talks about how to do useful things, how to build a testing infrastructure and quantum computing services and interfaces and all this stuff you can take away and you can use in your own projects and use when you get back to work or back to your desk. Well, I'm not going to give you anything here that you can use. I'm just hopefully going to give you stuff here that you enjoy, because there is another quote about art from another great British literary figure, which was this one. Douglas Adams, in one of his Hitchhiker's Guidebooks, says, "The function of art is to hold a mirror up to nature. Art gives us a tool that we can use to understand our world and our universe better. But before we can hold a mirror up to nature, we have to invent the mirror." And that is where science and technology come in. Because we have created scanning electron microscopes, which have allowed us to see things like this. These are tiny crystals growing on the eyelid of a beetle. They have been there the whole time. But until we invented microscopes, we'd never seen this before. These are silica crystals growing in a dish of soy sauce under an electron microscope. These are the spiral fronds inside the stem of a banana leaf. It's a world that's been hidden under our noses the entire time that human beings have been on this planet. And until we invented microscopes, we had never seen it before. And then we started sending cameras and satellites and people into space. And we saw our Earth, the pale blue marble. We looked back from beyond the rings of Saturn. You are here. This is us. And we've taken photographs like this one. This is the Pillars of Creation in the Eagle Nebula. This is 3,000 light years away from Earth. This picture taken by the Hubble Space Telescope, showing literally a factory where galaxies are born. And within the last 20, 30 years, we've started exploring another hidden world that is just filled with these amazing and wonderful things no one had seen before. A world of information and mathematics and technology. Throughout the 1970s, Martin Gardner wrote a monthly column in Scientific American magazine about mathematical puzzles. And this issue, October 1970, he described something called Conway's Game of Life. Now, John Conway was a British mathematician, and the Game of Life is a game for one player with 4 rules played on an infinite grid that you can't win. Great game, huh? Well, it turns out there's a lot going on in the Game of Life. The Game of Life has 4 rules. It's a game of cells, and every cell is either living or dead. And the rules of life are, if a cell has 0 or 1 neighbors, it will die of loneliness. If a cell has 2 or 3 living neighbors, it survives into the next generation. Cells which have 4 living neighbors will die of overcrowding, and cells that have exactly 3 living neighbors, they will mysteriously come back to life. And we're not quite sure why they do this, but they do. Those are the rules of the game. And in that original article. This is it. This is the whole of Conway's Game of Life. And in that original article, Martin Gardner sketched out these. These are the tetrominos. You probably recognize they're the Tetris shapes. And he kind of sketched out, well, this one does this, and then it does this, and then it does this. But looking at these on a piece of graph paper is like looking at butterflies in a glass case in a museum. You have no idea what they actually do. It wasn't until we got digital computers and we started running the tetrominos through those in the Game of Life that we started to understand how this system really worked. Because some of them stabilize very quickly, but one of them turns into this infinitely repeating crisscross traffic light pattern. And people started asking questions. Are there shapes that will just move in a straight line? It turns out, yes. Discovered something called the glider, which just glides across the infinite grid. One of the questions, are there configurations which will grow infinitely? It was the computer scientist Bill Gosper and his team. They discovered this in the late 70s. This is Gosper's glider gun. It's a pattern that emits a glider every 28 generations, just keeps looping backwards and forwards. They discovered another pattern, which was a thing they called the eater, which is a stable configuration that eats gliders. And now, we have a signal generator. We have something that can generate signals. We have something that can destroy signals. We have a 1 and a 0. We have Boolean logic. Can we use this to build logic gates? Take a look at this. This is our inputs, A and B, and this is our output, A and B. And if we set one of our inputs to true by taking the blocker out of the way, our output remains false. And if we set our other input to true by taking the blocker out of the way, give it a second to warm up, our output remains false. But if we set both inputs, A and B, to be true by removing both of those blockers, when we start running our Conway's Game of Life circuit, our output is now true. So we have Boolean logic and we can build logic gates. And if we can build gates, we can build circuits. And if we can build circuits, we can build computers. And if we can build computers, we can use those computers to run programs, like this thing you might have heard about a little while ago. It's a thing called Conway's Game of Life. If you want to know how that works, when you get home, look up the word metapixel. That's the secret to this. Now, John Conway actually died of COVID last year, and I like this. This was XKCD's tribute to him. But, so yeah, thank you, John. Now, the Game of Life is one of a whole branch of mathematical and information systems where very, very simple inputs and tiny changes can result in very, very different behavior. There's this thing you'll read about called the butterfly effect, which is to do with long-range weather forecasting. A butterfly flaps its wings in Beijing, and 2 weeks later we get sunshine instead of hurricanes in Los Angeles. Sensitive dependence on initial conditions. And one of the fields where this idea, the butterfly effect, really comes into play is complex numbers. Now let's take, we got a grid here, and we're going to draw a square here. This square is 2 by 2. What is the area of the square? It's not a trick question. You can count the squares if you want. 1, 2, 3. 2 by 2 is 4. And now we're going to draw another square, which is -2 by -2. What's the area of this square? It's also 4. So if 2 times 2 is 4, and -2 times -2 is 4, how can we make a square with an area of -4? Well, in reality, we can't because it's impossible. But this is not reality, this is mathematics, where we can do anything we like as long as we can prove it. And so mathematicians, when I tell you what, it doesn't exist, so we're just going to make it up. It's called I. It's an imaginary number that we invented, and it's the square root of -1. If you multiply I by I, you get -1. And everyone went, can they do that? And maths went, we can do anything. Look, we can prove it. Now, you take this I. Now, this is one of those things that kind of bakes people's noodles a little bit, but actually, it's not that complicated. We're going to draw a graph here. And what we've got here is the red line across the middle, this is real, and the blue line up the middle, that is imaginary, and that little point there, that is 0.8 of real stuff, and 1.2 of imaginary stuff. And now we are going to take that number, and we're going to do maths with it. We're going to square it. And we do this just like we did in school. We take the brackets, we expand them out, so we got this plus that times this plus that. Now, all you've got to remember is that any time you multiply two blue numbers together, the answer comes out negative. So we just keep crunching down that, and eventually we get a number, comes out the other end. So that top number squared comes out as minus 0.8 plus 1.92i. Now you know how to do maths with complex numbers. Now, in 1918, this guy, Gaston Julier, published this paper, Mémoire sur l'itération des fonctions rationales. Apologies, French speakers. I have not read this. It is 125 pages long, and it is in French, which, as you've just witnessed, I cannot speak or read. But I have read lots of stuff by people who did read this. And Gaston Julier was studying the way functions iterate. He wasn't interested in solving equations. He's like, what happens if we just keep running this thing over and over? What's it going to do? Now, if we take our real number line and we run x goes to x plus 1, it does this. And you're like, all right. And pretty much all of you now, you can be like, I know what that's going to do. I just instinctively understand the behavior of that system to infinity. If I know where it got to, I know what it's going to do. X goes to 2 minus x. Well, 0 goes to 2. 2 minus 2 is 0. 2 minus 0 is 2. 2 minus 2 is 0. We get these stable systems. X goes to x squared, 2 goes to 4, goes to 16, goes to 256, and off we go. If we start down here, 0.5, a half goes to a quarter goes to a 16th, a 16th goes to a 256th. So squaring real numbers is predictable. We know what's going to happen. See what happens when we square an imaginary number. So this is 0.7 plus 0.8i. We multiply it by itself, and it goes, I'm going to jump over here. And we're like, all right. And then it goes, no, I'm down here. And then it's going to go over here, and then it's going to go over here, and then, hey, it's gone, disappeared. And at this point, it's headed off to infinity. But now let's look at what happens. We're going to take a bunch of points in this plane. 0.9 plus 0.8i, bang, straight off. 0.8 plus 0.8i, straight off to positive real infinity. 7.8i, straight off to imaginary positive infinity. Now this one, it kind of bounces around a little bit, and then it looks like it's just going to go around in a circle for a while. And it bounces around, and it bounces around, and eventually it goes, nah, I'm bored, I don't want to be in this set of numbers here. And after a while, it will go whee and disappear off down to negative infinity. Now, these are 0.1 apart on the same grid with the same equation. Oops. The other ones, one of them disappears down the hole in the middle, one of them vanishes off, and it was this guy, Benoit Mandelbrot. Now, Mandelbrot was a Polish mathematician. His family grew up in France. He grew up in France. He went to the US. He had a cool job. He was one of the earliest computer scientists at IBM, and when he got bored of that, he went to Harvard and he taught mathematics. And so the Harvard maths geek would be like, can we do this? And he'd go back to IBM and go, I've got an idea for you, lads. And they'd run it on the computer, because they had one, and no one else did. And he was fascinated by the mathematics of nature. He had this famous quote, clouds are not spheres. Mountains are not cones, and coastlines are not circles. Bark is not smooth, and nor does lightning travel in a straight line. He wanted to understand the mathematics that made the natural world work. Now, he came up with his idea was, what if we take complex number z, and we iterate it to z goes to z squared plus c, where c is the number that you started with for each square on this grid. And he said, we're just going to run that over and over and over, and for each square on our graph paper, we're going to run it 100 times. And if the number goes to infinity, we're going to leave the square blank. And if the number hasn't gone to infinity after 100 iterations, we're just going to print an asterisk, because all they had to work with was a teleprinter, an IBM daisy wheel printer. And so they drew this shape. Each one of those squares, run it 100 times, and if it hasn't gone to infinity yet, plot a little asterisk and move on. And so he and his team, in 1982, they became the first people in history to see this, the Mandelbrot set. Now, computers have got better since 1982, citation needed. We have got color. We've got floating point coprocessors. We've got 64-bit arithmetic and GPUs. And the algorithm that we tend to use today is exactly the same, only we count how many iterations and we color code it based on how quickly something goes to infinity. So if it goes straight off to infinity, it's blue. If it takes a little while to get there, we go with purple. If it takes a long time to get there, it goes red. And if it never goes to infinity, we color it in black. And that is the algorithm that we use to draw shapes like this representation of the Mandelbrot set, which probably looks familiar to some of you. Now, the thing about this shape, From that, z goes to z squared plus c. And that little bit of complex arithmetic, there is an infinity of complexity in this. We're going to take this shape and we're going to start zooming in here. So that's our original. We'll say at this point we're at factor 1 magnification. So we're going to start zooming in. And this thing is going to start getting bigger and bigger and bigger. And round about here, we'll say, let's call that's factor 10, okay? And we're going a little further and a little further. And around about now, the original shape is the size of this room. And we're going to keep zooming in. And round about now, the original shape will be the size of London. And we're going to keep zooming in, and keep zooming in, and keep zooming in. Around about here, it's the size of the United Kingdom. And somewhere around here, the original shape is now the size of Europe. And we're going to keep zooming until the original shape is bigger than planet Earth, bigger than our solar system, bigger than our galaxy. We're going to zoom in to the point where something traveling at the speed of light would take a couple of hundred years to get from one side of the original shape to the other. And we're not running out of detail. Like, we haven't got anywhere close because there is an infinity of detail hidden inside that one equation. And if you go in far enough, you get this. You get self-similarity. It's not repeating. It's reminiscing. It is little kind of similar copies of itself all the way down. Now, somebody once referred to the Mandelbrot set as the thumbprint of God. I'm not a very spiritual person, but I play a lot of games, and I like finding Easter eggs in my games. And I like the fact that maybe, some benevolent designer, or just science being cool for a change, went, you know what? I'll put this there. When the monkeys have discovered the complex numbers and the imaginary numbers and the computers and everything, I'll leave this there just to tell them they're on the right track, and they should keep going with it. Now, just putting images on a computer screen, kind of big deal. That's a problem that we've solved now. In 1982, we had the movie Tron, which had these amazing computer-generated. This is way before Zuckerberg and the metaverse. This is when VR was still cool, right? And we had Luxo Jr., the first completely computer-generated cartoon. We had Jurassic Park in the 90s with these computer-generated dinosaurs sharing the screen with human actors. We had this guy a couple of years ago, Rogue One. Is this digital Peter Cushing, or is this Grand Moff Tarkin? Because one of those is a living actor is a dead actor with living descendants. The other one's a fictional character owned by Lucasfilm. Who owns the right to that character? I don't know. Ask a lawyer. I just thought it was a great movie. But computers can now answer all kinds of questions, like really important questions, like what would it look like if they remade Friends, but they cast Nicolas Cage in all the parts?
That was terrific.
Really bitchin'.
Now, if you're at TNG's session yesterday, you'll have got some insight into how they do this kind of stuff. This is Deepfake Technology based on training models and convolutional neural networks. And fundamentally, what we have been doing for the last sort of 10, 15 years is you ever lie on your back in a field on a sunny day and you're looking at the clouds and you're like, that looks like a house, and there's a rabbit, and there's a cat, and that one looks like my parents fighting. And what your brain is doing is it's running pattern recognition algorithms and is looking for patterns. Because as humans, one of the ways that we've learned to survive is we recognize important things like people and threats very, very rapidly. And we have started training computers to do the same thing just by giving them a massive stack of inputs and going, these are cats, these are dogs, you figure it out. And it runs layer after layer after layer of these learning models, and eventually the computer goes, yep, I think I know the difference between a dog and a cat, or the difference between a lamppost and a shadow, or, all these important applications. Now, it might not sound that difficult, to tell the difference between, say, a puppy and a muffin, right? But where things get good, where things get really good, is you take the dog detector that we have invented and you wire it in backwards. And you say, here is a photograph. Now, I took this picture when I got here yesterday, and I ran it through the dog detector, and it went, there are no dogs here. And I'm like, yeah, all right, I don't see any dogs. But then I flipped the detector backwards, and I went, no, there are dogs. Enhance the dogs. And the computer went, no. And I went, do what you're told. And it went, all right, I'm not sure about this. And I went, increase the power. And the computer went, you're not going to like what's about to happen. And I went, increase the power, fathomless deep dream level 16, boom. And I went, increase the power, and it went, are you sure? I went, yes. And I just kept cranking it up, and this is what happens when you wire a convolutional neural network backwards, is it looks for details that aren't there, and it amplifies them using things it's learned from its training model. So welcome to DevOps. I am dogs. We are frightened. And this is just a wonderful, this is to me a completely unique form of art that never existed until proper scientists did a lot of serious work to create neural networks, and then people like me wired them in backwards to see what would happen, because that stuff is cool. And we've seen so far a whole bunch of different art forms that are created by running code. But there's this question comes up, can code itself be art? Now, Donald Knuth's famous kind of 4-part masterwork, The Art of Computer Programming, says programming is an art form. And some people say we are software engineers, we are developers, we are coders. What is code? Is it an art form? Is it a science? Is it scripting? Is it hacking? Now, I've worked on a lot of teams, I've looked at a lot of code, and I've sometimes been sat there reviewing some code and thinking, I don't know what this is. It's not engineering. I'm not sure I'd call it art. It might qualify as typing if it wasn't for line 16 there. Fortunately, there is a place for these kinds of programs, which is the International Obfuscated C Code Contest. The goals of the contest are to write the most obscure or obfuscated C program, to show the importance of programming style in an ironic way, to stress C compilers with unusual code, and to illustrate the subtleties of the C language. Now, I went poking around looking for some interesting examples, and I found this, which I thought was, and I looked at it. Anyone want to tell me what this program does? Any C developers in the room? I don't know, so I did what any security-minded individual does with strange code they found on the internet. I compiled it and I ran it. And what came out was this. This is Flappy Bird implemented in a Unix terminal, and just like real Flappy Bird, it is fiendishly difficult to play. How about this? I'm going to zoom out, give you a little hint. So this is C code, and this is a Mandelbrot set generator written in ANSI C that outputs its code to the terminal. And that's what it looks like. That's the complete source code listing to that. Now, there are some fantastic examples of esoteric C and other languages as well, and some of these are astonishing in the level of minimalism that they achieve. This thing here, this is 1 kilobyte of JavaScript, and this is called NanoChess. It's written by a guy called Oscar Toledo G. And this, if you paste this into a text file and open it in a browser, it plays chess. It doesn't draw a chessboard, it plays chess. It beats me at chess in 1 kilobyte of JavaScript, which I think is phenomenal. Now, in about 1998, Simon Rasinkiewicz submitted this to the International Obfuscated C Code Contest with a README file saying, compile this with this particular C compiler. And that C compiler had a behavioral quirk. If you gave it an empty file, it would produce a valid program that produced no output. So he argued that this is a program that prints its own source code. And they said, very good, well done, have an award. And then they changed the rules so that you had to have at least 1 byte of input in your source code program. But this gets us onto one of my favorite things in the world of code and computing science, which is a thing called a quine. A quine is a program that prints its own source. The quines came from the idea came from this book, Douglas Hofstadter's Gödel, Escher, and Bach. And a quine is, it's a program that prints its own source. And just for fun, this, by the way, this is the first Java code I've written since 1999, and I decided to start with a program that prints its own source code. I thought, how hard can it be? So public class quine and static void, and I thought, okay, well, we've got the 3-quote string blocker quotes now, so we're going to need to print something. And then I thought, well, we need to print public class quine with a static void main, and then after that, we need to put a code in it, and we need to, this is never going to work, because it's just going to reference, it's an infinite loop all the way down. You have to cheat. You have to find the little loopholes that the language designers didn't think to close before they shipped it, like the fact that in Java, you can pass a format string to sprintf, and you can use that to say, I would like you. Now, if you look at this very, very closely, you see the $1 there? That means whatever the first thing was, I want you to do that again without me having to describe it in the format string. And then you can say, I'd like you please to print the code, then a closing quote, then a new line, then the code again, inject that into that format string, and then print that out. And that is a quine in Java. It's a Java program that prints its own source, on Java 17 at least, because I tried it yesterday. Now, there are quines in all kinds of languages. In JavaScript, this is a quine. Because in JavaScript, anything .toString, if it's a function, it tells you, well, here's your function back. I'm not sure why you wanted that, but you can have it anyway. And in ECMAScript version 6 and above, that's a quine. And I was like, no way is that a quine. So I pasted it into the console, and I ran it, and sure enough, that prints its own source code. So you do these in Java, Ruby, Perl, all kinds of languages. One of the interesting questions came up, can you do a quine in HTML? Can you make a web page that prints its own source code? Now, this guy called Leon Bambrick, secret geek on Twitter, who does some fantastic art as code projects. And I got the idea for this from him. So here's a web page, and here is the source code to that page. Now, the first thing that we're going to do is we are going to put in a style sheet rule that says display everything. Even stuff that's supposed to be invisible, display it as a block. And when we refresh, we can suddenly see our style sheet rule. That has come out at the top of the page there. Now we're going to put in some HTML pseudo tags. We're going to say, well, before the HTML, I want you to do HTML, and afterwards, I want you to do /HTML. We go back around. Now, /HTML is there, but it's actually here. Because where would you put it? You know, you've just said, when you're finished drawing your entire web page, put this at the end. It's like, where's that going to go? We'll fix that in a minute. We're going to put in a bunch more rules. We're going to say style before and after, and we're going to format it as white space with preserve wrapping. Now we're starting to get some of our code out. We're going to need to just paste in a whole bunch more of these before and after things. So there we go. And now we've got all of our HTML tags coming out. Now, we've got this link here that links to itself, links to Leon Bambrick's page. We can use CSS selectors and rules to inject the markup that shows where it's going into the page itself with this attribute href thing. And there it is. We have created a web page. We're going to add a little bit of formatting. Just put a margin on it, change the height of the thing, and there we go. That is a web page that prints its own source. It is completely useless, but I learned things I'd never learned in 20 years of web development by figuring out how to make all of that stuff happen. Now, let's take a look at this chunk of code here. What language do you think this is written in? C. Yeah, includes standard I/O, main. We take out the comments, we put some syntax highlighting on it. But what if we take the same code and we apply Ruby syntax highlighting? And we highlight the string literals as well. And that looks like a valid Ruby program to me. Only one way to find out, right? Let's run it, see what happens. So there is our listing. That's what it looks like. And now I'm going to run that thing through GCC. And I'm going to get the compiled output. Now, it's spitting out a warning. Kids, the time for warnings is long past. The safety is off. Okay? We run it in C, it prints its own source code. And now I'm going to take that same program, and I'm going to run it through the Ruby interpreter. And when I run it through Ruby, it prints its own source code. What else do I have lying around here? Well, Python's kind of cool. I'm going to run the same program through Python and see what I get out of it. And look at that. It prints its own source code. And I have an old copy of Perl somewhere in the cellar. Let's run it through Perl, and look at that. It prints its own source code. And it'll even print its own source code in C++ if you can find a compiler that doesn't care about the warning. And these days, most of them do, which is probably a good thing where C++ is concerned. This is a polyquine. This is a program which prints its own source code in more than one language. Now, take a look at this. What language do you think this is written in? Because there's a couple of clues in here, right? There's a system.console up there, which is a kind of like a .NET, C#, F# kind of a thing. And we got an XML, XSL transform namespace defined in there. If you know what that is, I'm sorry, we can have a drink afterwards. We've got a for each and a console.log, which smells kind of JavaScript-y to me. We've got an ADA text I/O procedure. We've got begin in block capitals, which is a business language like COBOL or SQL. And we've got Act 1, Scene 1, Enter Ajax, which doesn't look like programming code at all. This is an excerpt from Yosuke Endo's Ouroboros Quine. It is a Ruby program that produces a Rust program, that produces a Scala program, that produces a Scheme program, that goes all the way around the circle until you get an R program that produces a Rat4 program, that produces an RC, that produces a Rex, that gives you your original Ruby program back again. That's not the cool part. The source code to this, in its entirety, looks like this. That's not the cool part. This thing is future-proof. It has maintenance considerations built into it because the last 4 lines are a buffer for future bug fixes. That's not the cool part. This is the cool part. Every single one of those 128 languages you can install on Ubuntu Linux by typing apt-get, which means all of them are available in a container package, which means you can use GitHub Actions to compile all of them, which means there is a continuous deployment pipeline for the 128 language Ouroboros quine. That's the cool part. Now, backtrack a second. Act 1, Scene 1, enter Ajax. What is going on there? That, my friends, is a programming language called Shakespeare. And Shakespeare is designed to write valid computer programs that read like Shakespearean plays. The way the Shakespeare program, or the programming language works, you declare your variables as characters in a play. Your acts and scenes, those are namespace and scopes. So here we've got the infamous Hello World program. We've got Romeo, we've got Hamlet. Act 1, Scene 1, enter Hamlet and Romeo. Now, when Hamlet talks to Romeo, if Hamlet insults Romeo, Romeo's value is decremented. And if Hamlet compliments Romeo, Romeo's value is incremented. And so Hamlet says, "You lying, stupid, fatherless, big, smelly, half-witted coward. You are as stupid as the difference between a handsome, rich, brave hero and thyself. Speak your mind." And speak your mind is whatever's in the buffer currently, put that standard out. It's going to print H. You are as brave as the sum of your fat little stuffed, misused, dusty, yada, 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 yada. Shakespeare is not noted for brevity, either as a programming language or as a playwright. That will print E. By the end of the next page, we've got LLO. This is Hello World in Shakespeare across approximately 2 pages. What about this one? Anyone recognize this language? It is whitespace. Let's apply a little syntax highlighting to it. This is Hello World in whitespace. Whitespace is a language made of spaces and tabs, and everything else is a comment. And so if you need to hide a program inside another program, whitespace is a really good program to hide inside other ones because you can't see it. And yeah, this is Hello World in whitespace. All the instructions are combinations of spaces and tabs. Now, there is a programming language called Chef. And Chef is designed to write programs that are also recipes. And the canonical Hello World in Chef is the Hello World souffle, which has 72 grams of haricot beans, 101 eggs, 108 grams of lard, 111 cups of oil. Anyone hungry? Zucchinis, red salmon, Dijon mustard. Now, a couple of years after Chef was released, a guy called Mike Wirth sat down and figured out how to make a Chef program that was an actual recipe for an edible chocolate cake. And he did. And he shared it with some of his friends. And they said, it was a little dry, but if you execute this code on your kitchen, you get a cake with a chocolate sauce, and if you execute it on the Chef interpreter, you get Hello World. I love that idea. I love the idea that you can make a cake that no one realizes that's actually a computer program at the same time. I think that is fantastic. Now, on that note, let's have a look at how to square a number in the programming language called Pete. There you go. Pete is named after Pete Mondrian. It should have been called Mondrian, but Mondrian was already being used for a SunOS scripting environment, and so it's called Pete. Pete is a graphical programming language. This is a Pete program. The way that Pete works, the instruction set, is transitions from one color to another. So all of these things, if you go from one shade to another shade, that is considered an instruction. This is the color palette which defines the instruction set. And so the way squaring a number works in Pete, the instruction pointer starts at the top left, moving towards the right. So we travel from there to there, and that transition there, light blue to dark green, input a number. Prompt the user to give us a numeric input. Then when we hit black, you turn 90 degrees. So we're going to turn south, and when we cross from green into red, that means duplicate whatever is on the top of the stack. So now we have the same input on the top 2 points on our stack. When we cross from red into yellow, that means multiply, stack operation, take the 2 numbers off, multiply them, put it back on the stack. Yellow into dark red is output whatever number is on the stack there. Then when we cross into white, white is a no-op. We get to blue. Blue is a no-op because it's the edge of the grid, but we turn 90 degrees. We keep going until we have black on all sides. That is Mondrian's way of saying halt. You've reached the end of the program. Now, hello world in Pete looks like this. And you could print this out and hang it on the wall in your house. And no one would have any idea that they were looking at hello world. They just think that you like kind of slightly weird pixel art, right? Now, I love these ideas. I love the idea of software and code which looks like an art form from a completely different medium. And over the last couple of days, we've seen some really excellent talks here. And I've seen quite a few talks where people did live demos. And live demos at a conference like this, they're always exciting, right? Because there's this element of uncertainty. This risk, is it going to work or not? It's like watching a high wire act, someone typing this, and the audience are kind of helping out, and there's always this, is it going to work or is it not going to work? And that's what makes these things, presentations exciting, is that element of audience interaction, but it's also unpredictable. And, as engineers, we hate unpredictable. We want things to be the same every time. We want infrastructure as code. We want everything replicated and backed up and reproducible. We use Snowflake as a derogatory word for, oh no, that's a Snowflake server. If you put Windows Update on it, no one gets paid this month. Don't even breathe in the same room as that server. But, in nature, supposedly every snowflake is unique. Which means if you go out in a blizzard and you pick a snowflake out of the air and you just watch it melt on your hand, you have just been part of a unique experience that nobody else will ever participate in. And that, to me, is what's amazing about live performance. Now, this is the Royal Albert Hall here in London, and this is the London Philharmonic Orchestra, and the guy over there, set up underneath the big screen, is Sam Aaron, and Sam created a program called Sonic Pi. And Sonic Pi is a musical programming language designed for Raspberry Pis so that kids can get like a 10-pound computer or plug it into the TV and they can start programming with this thing. And Sonic Pi is fantastic. I'm going to do a little quick demo for you now. It's not a live demo. It's a canned demo, but you'll see why. Now, Sonic Pi, its basic instruction is play. It plays a note. Sonic Pi is the only programming language that runs all its instructions in parallel unless you tell it not to. Imagine if Java did that, right? If you want to play notes one after the other, you have to put in sleep statements. But this is a full-blown programming language. It has loops, it has variables, it has conditionals, it has branches and instructions. Dun, dun, dun. Now, this is not terribly exciting. It's a little bit funereal, right? I'm going to kick things up a notch. So what I'm going to do here, I'm going to say we're going to use beats per minute, 244, and then I'm going to change that sine wave noise, and I'm going to use a synthesizer noise we got in here called tech saws, which I happen to like because I like 80s synthwave and that kind of stuff. And there we go. All right, now we're getting somewhere. So now what we're going to do is we're going to take that loop, and we're going to start doing things with it. So we've got our loop running, and we're going to turn that into something called a live loop. Now, under the hood, Sonic Pi is running on an Erlang audio engine called Super Collider, which is just unbelievably cool. And I'm going to write another loop. And I'm going to say, sync this loop with the main loop, and 15 times I want you to play this drum cymbal closed, which is like a noise, and sleep. And then, you hear that? Now I'm going to copy and paste some more drums, which I prepared earlier. So we've got a kick drum and a snare drum in there. And I'm going to drop that in. You notice we never have to restart the program. This just keeps going over and over and over. And we can drop these loops in, we can take them out. And now, I'm going to put a counter variable in our main loop. And I'm going to say, all right, we're going to count with I. And if I divides by 3, I want you to play this note instead. And if I divides by 5, I want you to play this note instead. Does anyone remember, like, loops where something divides by 3 and divides by 5? And maybe if I divides by 15, we want you to play this other note instead. That's Fizzbuzz, implemented in Sonic Pi with musical output. I call that thing the Fizzbuzz riff. And watch out for it, because we're going to be hearing from that again before the day is out. Now, so far, all the stuff I've shown you is cool stuff that other people did. And, brilliant projects by some incredibly talented and just unbelievably gifted engineers and programmers and scientists and that kind of stuff. I want to finish up by telling you about something I did. Now, There is this trope that exists in the world of technology about rock stars, right? You go on LinkedIn or you go on IT jobs and you search for Rockstar developer, and you will find people who are trying to hire rock stars. And there are Rockstar JavaScript engines. I believe there's a thing called a Java 1 Rockstar, which is where you've written the base class library and sold 50 million records or something. But you go on and there's, well, we want a Rockstar database administrator. We want a Rockstar this, we want a Rockstar that. And no one really knows what a Rockstar developer is supposed to be until a couple of years ago, somebody put on Twitter, to really confuse recruiters, someone should make a programming language called Rockstar. And I had this experience. I had a moment of divine inspiration. Now, when I saw that tweet, I was in a bar. I had beer and I had a laptop and my friends weren't there yet. This is a bad combination when it comes to designing programming languages, because I thought, obviously what the world needs is a programming language based on 1980s hair metal songs. That's what's missing from all of this. And so I got my laptop out, and I started writing a parody language specification. And I thought, all right, Rockstar, what is it? It is a dynamically typed Turing-complete programming language heavily influenced by the lyrical conventions of 1980s hard rock and power ballads. Now, I'm going to give you a little lesson today in Rockstar syntax. First of all, hello world. Now, this language needs to be kind of easy and approachable. So if you want to say hello world, you just say hello world. Or you can scream it. Or you can whisper it, or you can shout it, because we're not just writing programs here, we're writing songs. You want to tell people how you're feeling that day. Now, you can't write a program without variables and assignment. Now, if you're using strongly typed languages, int x equals 5 semicolon, var my underscore string equals hello blah blah blah, var the message equals devox rocks. Now, let's go dynamically typed, and also we're going to get rid of the semicolons, because, you know, if Ruby and JavaScript can live without them, so can we. Boom, gone. Next up, we got this sort of slightly awkward equals in the middle there. Now, when you listen to people talk, they'll say things like x is 4, y is 2. All right, is. Perfectly good English word. X is 5. My string is hello world. The message is devox rocks. And then you're looking at this and you're thinking, well, my underscore string, that doesn't sound very rock and roll, does it? And is that the message? How do you sing that? Now, I saw Douglas Crockford give a talk called The Post-JavaScript Apocalypse, where he basically talked about all the mistakes that are so baked into our DNA as developers we don't even think about correcting them. And he asked this question. He said, how many of you have ever had an argument longer than an hour about whether to use Pascal case versus camel case versus underscores versus? And it's like, yeah, and he's like, what we want are variable names with spaces in them. Like, that's why we have these arguments, because we can't put spaces in our variable names. Now, when you're inventing a programming language in a bar, you can do anything you like, right? It wasn't a complete free-for-all. I did put a little bit of thought into this. And I thought, all right, what if we had simple variables work like they do in most dynamic languages? Common variables have to have one of these prefixes. Say, my heart, an ocean. Proper variables have to take capital initials on every word of the variable. Now, declaring numbers is a problem, because generally songs, other than a 1, a 2, a 1, 2, 3, 4, if you put lots of digits in a song, it starts sounding a little bit weird. But I wanted a way to initialize numeric variables, because I needed to be able to write Fizzbuzz, so that people could do interviews for Rockstar developer jobs, right? And I'm like, well, 3, 5, 100, what if we take words, and we count the number of digits in each letter, modulo 10, and treat those as the decimal digits in a numeric literal. So fizz is ice, buzz is dying, the limit is a love-struck lady killer, gives you 3, 5, and 100, right? We needed a way of declaring floating point numbers. Now in C#, decimal pi equals 3.1415, and in JavaScript, 3.1415, and after that, really, you're not going to get the same number back out, so you might as well stop adding precision to it. In Rockstar, you initialize pi by saying, my heart was ice, a life unfulfilled, waking everybody up, taking booze and pills. Ice, 1, 2, 3, the dot is a dot. 1, 4, 9, 5, 9, 2, 5, 5. We needed arithmetic. Now, you listen to people talk about maths in English. How much is the bill? It's the price with the tax. It's the total without the tax. It's the quantity of the product. Speed is distance over time. Those are our arithmetic operators. Or a girl with a dream, a man without a face, the wings of the night, a whisper over the water. Math just got cool, right? Comparison. Your love is a lie, true or false? The whiskey ain't the answer, true or false? My heart is stronger than steel, my soul is weaker than water. My will is as strong as a lion, your lies are as low as a snake. I needed a function syntax. Now, listen to people talk about functions. They're like, okay, so a function here, we got a modulus function that takes a number and a divisor. And while a number is as high as a divisor, put the number without the divisor, basically the repeated subtraction method of doing arithmetic modulus, give back a number. Or, midnight takes your heart and your soul. And while your heart is as high as your soul, put your heart without your soul into your heart and give back your heart. At this point, I'm like, it's done. We can do Fizzbuzz in my parody spec. I finished my beer, I put a thing on Twitter, I went to bed, I got up in the morning, the internet had found this, and it had gone wild for it. It made a front page of Hacker News. It made a Boing Boing, Cory Doctorow did a write-up about it. It made Reddit. People on Reddit were saying nice things. Like, people on Reddit don't say nice things. The docs are hilarious, shut up and take my money. Then I got an email that I did not expect from Classic Rock magazine, which has nothing to do with stupid programming jokes. They normally interview, like, you know, Motley Crue and Scorpions and Metallica. And like, what's this Rockstar language everyone's talking about? And they did a feature on it. And I got in Classic Rock magazine for inventing a joke programming language, which I'd love to go back to 16-year-old me and tell them that they made it in Classic Rock and not tell them why, you know? But then things got really weird because people started filing issues against my parody spec on GitHub. And you know, some of them were like, some of it was people implementing stuff. Other things was like, there's undefined behavior in your spec. What happens here? I'm like, why do you care? And I'm like, because I'm building a Scala, a Rockstar Scala transpiler. And I'm like, you're doing what? Within a week, there was a Rockstar Scala transpiler, there was a Rockstar Ruby transpiler, someone had written an interpreter in Java for this thing. People just kept kind of throwing ideas and enthusiasm and projects at it. And of course, this is me going, I wish I hadn't invented a language in a bar. Because there's a couple of little details in there which actually proved horribly, they were fun jokes at the time, they were horribly difficult to implement. And eventually I decided I wanted to get in on this action. So I took a couple of weeks off, and I remembered how to write compilers, which I'd learned at university and then promptly forgot as I left the room from the compilers exam. And I built a Rockstar interpreter in JavaScript. I did it in JavaScript for one very important reason. I wanted to be able to run it on a phone in a web browser. So if you go to codewithrockstar.com right now, you can type in a program, and you can click rock, and it will run your program. And if it works, you can come up and see me after the talk. Now, the logo, by the way, the top left, that Rockstar logo, I wanted something that was, you know, completely 80s synth glam metal over the top, and I kind of looked at some band logos and went, none of this is crazy enough for me. And then I found this, the Microsoft Consumer Products logo, 1982. And they weren't using it anymore, so I recycled. So thank you very much, Microsoft, for letting me reuse your old logo. Now, if you want to write some Rockstar code, do it now on your phone. If you come up and see me at the end, I will give you your self-adhesive, certified Rockstar developer certification. But I'd like to close out DevOps now by, you've seen the program that's actually a chocolate cake. And you've seen the program that's actually Hello World that you can hang on the wall and people think it's art. And what I'd like to do now is to perform Fizzbuzz in Rockstar for you and see if you think this qualifies as a bad 80s heavy metal song. Like, we're not going for Grammys here. Like, the B-side of a Meatloaf record is kind of the artistic level that we're supposed to be shooting for here. So, I'm just going to upgrade my hardware here. You can do these things virtually, but it's not nearly so much fun. There we go. Okay, that works. Friends, DevOps, I give you Fizzbuzz in Rockstar. your heart and your soul. And while your heart is as high as your soul, put your heart without your soul into your heart. Give back your heart. Listen for Fizzbuzz. Thank you very much, Devox. Damn, it's good to be on a real stage again. Thank you so much, everyone, for coming along, to all the speakers, all the sponsors, everybody else who has come along and made all of this happen. I am definitely going to be sticking around. Is there a plan for drinks afterwards? Because if there isn't, I can make one.
Make a plan, Dylan, make a plan.
All right, come find me in a second. I have some Rockstar developer stickers and assorted other swag, so please come down when we've wrapped up. Come down and grab some of those at the front. Thank you very much, everybody.